Can you make your paper? You should first switch it to June.
Good morning. I'm Shingo Gibo from Japan. Today's journal topic is the relation between chemical reaction rate and temperature. First, let's read abstracts. Did you finish? Okay. So where is the gap sentence? It's not here at all. The gap sentence. Or maybe sentence is also gap sentence, but it's example. General gap sentence is correct line. They wrote many examples in abstract, but generally they claimed the reaction temperature dependence of the reaction rate at network level is abnormal. It's the problem. Then, generally, increasing temperature accelerate biochemical reaction. For example, in cold refrigerator, food keeps fresh under cold conditions. But in hot summer room, food goes worse very soon. So there is a general theory about the relation between temperature and reaction rate. It's called Arrhenius equation. This formula is derived from statistical physics. So this equation is based on theory. Theoretically, there is theoretical validation. And to understand this equation, this Arrhenius plot is very useful.
Could you explain the Arrhenius equation? And then clearly.
Okay. The,
Yeah,
Okay.
there is, you should explain.
okay. K is a reaction rate, and T is absolute temperature, and A and KB and E are constant value. And it means if the temperature is high, this exponential function becomes large, and chemical reaction is higher. This I didn't follow exact derivation, but the philosophy is the chemical reaction occurs if the potential value, if the potential barrier, if the energy is higher than the potential barrier. So in statistical physics, this distribution follows Boltzmann distribution. So we can write this relation as the Arrhenius equation. And then to understand this formula, this poster is very useful. Horizontal line is 1 over temperature, and vertical line is log of chemical reaction rate. And the left side is hot, and the right side is cold. So the log of reaction rate equal minus E over KBT. It means if the reaction rate follows this equation, this plot is the decay linearity straight line. And this theory is
So, okay. So next. So, when you see this kind of graph, I know, yeah, it's linear, it's beautiful, but how we understand this kind of relationship intuitively is here we didn't do anything. At 1 over T, I know 1 over temperature, but we can think that this is temperature. But here we apply the action log. What that means is here is an additive. Here addition becomes addition of the y-axis, right? Because it's linear. If we increasing by 10, then here will be decreasing by the 10. But there's a log. So what is a plus and minus in the log? It's a multiplication or division, right? That means if we increasing some temperature in terms of addition or subtraction, the reaction, log of a reaction is changed by plus or minus, right? That means inside of the log, actual reaction rate is changed by all the change. Do you understand? So if we increase the temperature, for instance, by 10 degrees, then the reaction rate will become faster by like a 3-4 or 4-4. Do you understand? So when you see the log in the certain axis, just if you understand, okay, x is some value and y-axis is log, or there is linear. Yeah, I know, even middle school students understand it, but that's not understanding. So actual understanding meaning is you should understand what's really going on. Okay, so when you look at this, x-axis is changed by plus minus. Good. So it's like your bank deposit. Have you ever experienced your bank deposit is changed by fold in your life? Plus minus or fold change?
That's my
Yeah, typically plus minus is it. correct? But like the y-axis could be like if you do like a Bitcoin is not the plus minus. It's changed by usually fold, right? Do you get the point? So you should get that feeling. In the real life, temperature changed by plus minus 3 or 10, right? But reaction rate itself is changed by some fold, different scale. That's the key point of the Arrhenius equation. You get it? Good?
Yeah, thank you. And this theory is experimentally validated. It's the oxidation reaction. The Arrhenius plot is clearly linear. So the Arrhenius equation is theoretically and experimentally validated for a single reaction. It's a single reaction, but the network level is unknown. And there is an experiment of complex systems. It's the development of Drosophila embryo. Yeah. Let's see the shape of the embryo changes with time, like this. And the upper panel is the snapshot. Yeah. And right figure is the Arrhenius plot of the developmental system. X-axis is 1 over temperature, and the y-axis is log of 1 over time. In this case, time means time interval from stage A to stage K.
So what that means is when we have a single cell for the Drosophila, as time goes, it's dividing, become growing up, right? So as temperature going down, that process will become slow down and slow down, slow down. Or velocity become smaller and smaller. It's a very universal phenomenon. Actually, same for you guys. Because your mom's body temperature is maintained at 37 degrees, that's why you've grown up in a similar speed in the mom's body. But theoretically, if we can decrease your mom's body temperature 10 degrees, then you should stay in your mom's body and it's twofold high. Something like that.
Thank you. So, but in this experiment, the Arrhenius plot is not linear. It's the shape is non-linear, and then this experiment follows quadratic function rather than linear function. Log of likelihood of quadratic function is much larger than linear function. So this reaction rate doesn't follow the Arrhenius equation. In numerical simulation of random network, even if each reaction rate follows Arrhenius equations, the Arrhenius plot is like quadratic function. So for each single reaction, the Arrhenius equation is valid, but network level, the Arrhenius law is violated.
So the summary is each reaction has a linear relationship.
Yeah.
However, when they merge it together, the total output follow this quadratic. In particular, what is a quadratic is okay. What's the most non-intuitive thing to you guys in this quadratic?
If we increase temperature more and more, then it will decrease, the reaction rate will be decreased.
Which part is non-intuitive to you
I don't
among
know.
this axis? Where? Left side or right side? Yeah. This side is nonsense, isn't it? And the temperature going down, everything is going down. But for this zone, total output speed is increasing. So we clearly say that every single reaction is going up, go down. For total output, for instance, this development is up. What do you think? Trivial or not?
네.
뭐 아무튼 그 경향성이 뭔가 반대 맞나?
뜨거워지면 뜨거워질수록
어.
리액션 레이트가 내려가는 부분이
그러니까 이게 맞는 거. 이게 자연스러운 거 같아. 지금 RNAS 이퀘이션 이거니까. 그러니까 이렇게 되는 건 난 괜찮은 거 같아.
네네네.
지역이 이상.
네네네.
맞나요? 동의? 그러니까 뭔가 직관과 anti-intuitive, isn't it? We slow down everything or we speed up everything, but total behavior behaving opposite way. Kind of what that means is, in my lab, I ask you, we have a deadline so that every member speed up, but everyone, well, total output become slow down. Do you like it? That happened. It's weird. Everyone working hard, but number of publications become reduced. Yeah, that's what happened in biology for some certain reason.
Yeah, right.
So Shingo, when you give a talk, for instance, typically this is research. This is a key.
Yeah.
When you tell something to the people, if there is non-intuitive, very interesting point, you should highlight.
Oh,
You get it?
thank you. As Professor said, the left side is non-trivial. So, and so far, there isn't general theoretical framework to analyze this. In this paper, to analyze the temperature dependence of chemical reactions at the network level, the authors developed a graph theoretical approach. By using graph theory, they analyzed this relation. Their method is called mean first passage time. For example, here is the chemical reaction network, and vertex 1 is initial position, and vertex 4 is target. For the previous developmental system, you imagine vertex 1 is stage A, and vertex 4 is stage K, final stage. And the settings of the problem is here. First, set up the directed chemical reaction network with n+1 vertices. The vertex is interpreted by chemical species. And then particles move randomly on the network. And the initial position is vertex 1, and the target final position is vertex n+1.
In this example, n+1 is 4.
N+1 is 4.
Our goal is we begin from the stage 1,
Yeah.
and we want to reach to the stage 4.
Right. And for example, some particle passages like this, and some particles skip vertex 3, and some particles repeatedly, and then finally reach vertex 4. And then mean first passage time is average time to first reach the target. Maybe first passage time of this path is short because it shortcuts the vertex 3. And for this path, first passage time is long because it's repeated the same way. So one of our goals is calculate this mean first passage time. To do so, we consider chemical master equation. Master equation means the dynamics of probability density function. And generally, master equation can be written as this. The first term is incoming edge, and second term is outgoing edge. And for final target vertex, it's not outgoing, so only the first term. And initial condition is only P1 is 1,
Okay.
and the other vertex is 0.
Please note that here Pi is probability. Okay. So we have only single molecule here, which begins at position 1, and then the probability that we are at a certain position I is between I.
Then, by analyzing this master equation, we derive the mean first passage time. But the derivation is complicated. So first, let's consider the simplest example. Simplest example is single reaction. Only there is only one reaction. In this case, master equation is simply linear equation. So you can easily derive the exact solution. The exact solution is exponential function. And then probability that the particle reaches vertex 2 in the interval between t and t plus dt is written here. It's the difference between p2 of t plus dt and p2 of t, because this probability is the particles reaches at the target state between this interval. And P is probability density, so P2 must be 1 minus P1. So this probability is related to P1T minus P1T plus dt. And then mean first passage time is summation of P times this probability. And if the dt is sufficiently small, the difference becomes derivative, and the summation becomes integration. And then by using integration by parts, this equation can be written in this equation. And P1 is exponential function, so P1 of infinity is 0. So the first term disappeared. And then mean first passage time is simply integration of P1 of T, P1 of T.
Well, everyone is okay about this? Can you understand this? Mean first passage time is which kind of, let's ignore this. You can plug in this way. T times this summation over the T. Is it intuitive for everyone? So step by step. So probability that a particle reaches vertex 2 in this interval is this. Is this correct? One minus 2. Okay. So let's delete that. Okay. So what that means is, I think what that means is probability that the particle reaches vertex 2 in the interval here for the first time. Then does it make sense? Why we subtract the P to T? So it should not reach until to the time T. So I think that's why we subtract this. Then we should reach at the T plus dt. So that, okay. I think here missing is for the first time. Happy? Then what is the meaning of that? T times this. We are reaching T plus between T and T plus delta T, but delta T is very small. So that basically what this means is we are reaching to the vertex 2 at time T for the first time. This is probability that we reach to the vertex 2 at time T for the first time. Good. Then what is the mean passage time? Mean passage time is what is the average time? Average first time, right? Then how we can calculate it? Then T times probability that this first passage time is T. So T times this. Okay, so here first time is missing. Then this equation is understandable. Good. Okay.
Thank you. And then we know P1 of T is exponential function. We already obtained exact solution. So we can easily calculate this integration. So then we understand the mean first passage time is 1 over reaction rate. It makes sense.
Everyone makes sense. K1 to become faster and faster. That means bus is coming faster and faster.
Yes.
Then the waiting time for the first bus is shorter and shorter. Clear? But everyone, please note that when you explain certain complex concept, this strategy used by Shingo is very useful way. Using the most simple example, and then illustrate that. This is very, very important for the good presentation.
And then I think you understand the simplest example.
But then we understand the complexity. And it's we pretend.
But next we don't consider complex.
Yes.
Next, we'll consider another simple example. It's three component, 8. So the network effect arises. The master equation is here. And yes, the same formulation. And these are probability functions. So P3 is 1 minus P1 minus P2. So we don't need to consider P3. Analyzing P1 and P2 is sufficient enough.
Okay.
So we will analyze only P1 and P2. And then P1 and P2 are also linear equation, linear differential equation. So we can obtain exact solution by using eigenvalue and eigenvector. And then probability that the particle reaches the vertex 3 in this interval is the same formulation. It's P3t plus dt minus P3t. And it's rewritten summation pit minus pit plus dt. It's same formulation. And then mean first passage time is summation p times this probability. And if the dt is small, the summation is integration, and the difference is derivative. And then using similar analysis, we obtain the mean first passage time is summation of this integration. And we know pi is the exponential function. Yeah, we know exact solution of P1 and P2. Then we can obtain this equation. So it means K21 is backward reaction. So it means due to the backward reaction, the mean first passage time becomes longer. It's network effect. And then what we want to know is the network level reaction rate. And the analogy of single reaction, network level reaction rate is 1 over mean first passage time. Then, and we know mean first passage time, the network level reaction rate is this equation. And then we assume each single reaction is assumed to follow the Arrhenius equation. We can obtain the temperature dependence of reaction rate. Here is the results. This network structure is not complicated, so it's similar to Arrhenius model. Red line is the network level reaction. we derived. And black line is simply straight line with RNA, with power RNA equation. This network structure is not complicated. So the red line, black line is similar, but slightly different from, slightly deviated from RNA equation. So this deviation is the network effect. So the result of this simple network is at the network level, the temperature dependency of the reaction rate deviates from the RNA equation, even if each reaction follows the RNA equation. So you can analyze the simple network. And then we want to analyze more complicated network. But the problem is to theoretically analyze the network level reaction rate. Is the exact solution of the master equation required? In this derivation, we use exact solution. You know, the exact solution is exponential function. Is it necessary? The author says no. Using graph theory, we can derive the network reaction rate without exact solution. And next, I'll explain the generalization of this analysis. We consider N+1 component network. But the formulation is same. The master equation is here. It's the same. And then Pn+1 is 1 minus summation of Pi. So we analyze the first equation. And then to do so, we use matrix representation, but it's the same meaning. It's for calculation, we represent the matrix formula. And P vector is the vector is P1, P2, Pn. And matrix K is the coefficient matrix. K contains the information of network structure. And then we can write formal solution. We don't need to derive. We don't need derive the exact solution, but for later analysis, we put the formal solution as here. P1 of P is equal exponential Kp times P1 E1. E1 means EI means elementary at the unit vector. So P1 is 1, 0, 0, 0, 0. It corresponds to initial condition. Initial condition is on P1 is 1 and the others are 0. So exponential function times initial condition is the formal solution. And then ith component of P1 P is right here. It's multiply column unit vector. So we can write ith component of the probability density vector. And we know p vector is exponential k3 times v1. Oh, okay.
Everyone, is it trivial to you why we multiply the E1?
So it's the initial condition, right?
Yeah, it's initial condition.
Initial conditions. P1 is 1.
Yeah.
I see. So we remove the n plus 1. Okay.
Yeah.
Okay. So initial condition was P1 is 1, other thing was 0. So that what is the differential equation solution? Exponential times initial condition. Here initial condition is 1, 0, 0, 0, 0. If we begin from the second position, then we should multiply the 0, 1, 0, 0, 0. Everything is clear? Make sense? Okay, next.
And then ith component can be written here. And p vector is exponential kt times e1. And it's similar. We take transpose matrix and the order is opposite. It's the same meaning. And the mean first passage time is here. It's the same formulation, but the summation is from I equal 1 to n. And it's becomes summation becomes integration, and difference becomes derivative. And then for the same reason, mean first passage time is the summation of the integration of PIT. And we know Pi of t can be written using exponential matrix function. And then take summation mean first passage time is this column vector times integration of exponential function and 1. One vector is all components are 1. And then this integration can be analyzed like here. So this integration is inverse of minus k transpose. So mean first passage time is simply column vector times this inverse matrix and one vector. So K matrix contains network structure. So we use the solution of P1 the vector. For the conclusion, we don't need to use the exact. We don't need to solve the exact solution. It's simply calculate inverse of minus kt. So you understand, if given the network structure K, we can derive the mean first passage time. And then how do we calculate this inverse matrix? And you can write down every component. And the mean first passage time becomes this summation of 1j component of inverse of minus kt. And according to basic linear algebra, the inverse matrix can be written here, minus 1 to I plus j over determinant minus k times mji is a cofactor. It's defined this determinant of minor matrix. You may think it's complicated, but it's not so difficult. It's from basic math. So it's I think it's complicated, but not difficult. Then mean first passage time is a summation of minus kt. So it's given here by here. So you can derive the mean first passage time by your hand. But it's very hard work. So to compute this numerator and denominator, they applied graph theoretical approach. So far, we don't use graph theory. And from next slide, we use graph theory. According to graph theory, according to generalization of Kirchhoff theorem, the determinant can be written here. But this E of n plus 1 is called spanning tree rooted at n plus 1. The definition is all vertices are connected with no cycles. And for any vertex, there exists a directed path to vertex n plus 1. Yeah, it may be difficult, but we see the example. There's the example for component network. Spanning trees are here. For this spanning tree, all components are connected. All vertices are connected, not separated. And there is no cycle. It's all straight. And the second definition is from any vertex, there exists a directed path to vertex n1. It means if R starts from vertex 1, it reaches vertex 4. If R starts from vertex 3, it finally reaches vertex 4. And for example, other in this graph, if we start any vertex, this path finally reaches vertex 4. This is the definition of the spanning tree. And then double T means product of reaction rate in the this subgraph, it means, for example, for this graph, WT is K14 times K24 times K32. And for this subgraph, WT is K14 times K23 times K34. So you can calculate WT using this graph. And then the determinant is summation of this WT. And then you can check. You can check. Yeah, but I already checked. Yeah, the determinant can with this term, and I already checked. This determinant is summation of this WT. So using this theory, you can obtain determinant of minus KT from this subgraph. So yeah, we can analyze this determinant. And then next, we want to know this summation cofactor. It's also obtained from graph theory. It's use this formula. Minus 1 to 1 plus j times nj1 is equal to this summation. And the subgraph 1 jn plus 1 arrow j is equals spanning forests. The definition is vertex 1 and vertex n plus 1 are disconnected. Vertex 1 and vertex n plus 1 separate, not connected. And then one tree contains vertex 1 and is directed toward vertex j. For example, in this case, its j is 3. And for neglect, right, like 3. And for example, this subgraph contains vertex 1 and it reaches vertex 3. And for example, for this example, it contains vertex 1 and reaches vertex 3. And same. For this case, it also contains vertex 1 and directed vertex 3. And third definition is the other tree is directed toward vertex n plus 1. For example, in this case, the other tree is here, it's directed vertex 4. Or more complex. For this case, vertex 1 and vertex 4 is separated, and the other tree reaches n plus 1. That is the definition. And in this case, weight matrix is here. For this case, WF is K24 times K32. In this case, K23 times K34. And the summation of W is cofactor. It also, I checked, it's true. Actually, this cofactor is determinant of this matrix. It's two by two matrix, so easily analyzed. And actually, summation of this coefficient is equals this determinant. And for other case, it actually corresponds to these equations. So I couldn't prove the general formula, but I checked this example, and it's true. It's correct. So this. So using these subgraphs, using spanning forest, you can obtain this cofactor matrix. And finally, what we want to know is mean first passage time. It can write. It can be right down here, and then, as we saw in the previous slide, the determinant and the cofactor can be written by using spanning forest and spanning tree. The denominator is summation of coefficients of the spanning tree. So you can obtain using this determinant using spanning tree. And notably, in the graph theory, there is efficient algorithm to find this subgraph. It's called Wilson's algorithm. So far, I didn't check this algorithm work correctly, but Gyosa said there is algorithm. And then numerator can be calculated using spanning forest, summation of spanning forest. And in this paper, the authors have proposed an algorithm to find spanning trees. I didn't check it works correctly, but if I believe, we can find spanning trees and spanning forests, and using this information, we can derive mean first passage time. And then network level reaction rate is 1 over mean first passage time. So the definition of W is where the summation of product of reaction rates. And then, assuming the Arrhenius equation, we can analyze the temperature dependence of the network level reaction. It may be complicated, but you can analyze, you can obtain the reaction rate using graph theory. And this is the first main conclusion of this paper. Yeah.
Okay. So when we do this, do we know the matrix K?
Yeah.
So why?
If matrix K is given, you can obtain this equation. Only if we know matrix K.
So I'm wondering if we know the matrix K,
Yeah.
we can just calculate determinant and vector.
Yeah.
And in the case, do we still need that graph tools,
Graph two.
that
Yeah.
the graph formulation,
Yeah.
we still need it when we know the matrix K?
Yeah. You can apply. You can apply this graph theoretical approach.
I wonder why. I wonder because
I think that is much faster than the calculating.
is it?
Yeah. They didn't compare the computational costs, but I think this approach is faster. But
I just imagine that finding the spinning tree and spinning forest would be very slow. So I just wonder.
Yeah, we need to compare the computational cost, but I don't know that. If directly calculation is faster, you can you can analyze directly.
And they put some another algorithm to find them.
Gibo, I have a quick question.
Okay.
So capital N is equal to the dimensional transition matrix that A.
Yeah.
Then N is equal to dimensional matrix that
Yeah.
transition.
Yeah, and so the matrix K is n by n by matrix.
Okay, thank you.
Any other questions?
Is T always invertible?
Always.
If not, then which graph case is most?
If determinant K is 0, its K matrix is singular, so we don't derive the inverse matrix. But in this formulation, we can calculate spanning trees. So
가운데 항상 마이너스 시그마. If the diagonal terms are minus of other column sum,
Yeah, implement response should be the calculation.
then inverse. What do you think? That form guarantee the inverse or not? We learned it long time ago. 그러니까 이거 모르겠네. 아니면 뭐 이렇게 연결이 안 돼 있으면 안 되나? 화성까지 가는 길이 아예 없어. 생각도. Maybe that the path is disconnected. Singularity.
yeah. That's right. Maybe the network is disconnected. Column or row is 0. So in this case, the matrix is singular. So, but all all components are connected, this matrix are not singular. And then there is spanning tree.
Maybe in that case, we can find some soft network
Yeah,
that can connect it to our final
yeah.
definition. And maybe we can calculate them. Do the same thing to calculate
Yeah,
the
right.
first process.
Right, I think so. Thank you for the very important question. Then, any other questions?
연결이 돼 있어요. I don't know. According to the Gemini, if there is a connected, then input. And all graphs are connected. So there should be a pattern to the end.
Any other questions? No question. This is the first part of this talk. It will be second part. Now we understand the graph theoretical approach is very useful, but there is problem. Real biological systems often consists of large biochemical network and maybe 100 or 1,000. In this case, there is problem. The number of spanning tree grows faster than exponential function. It grows n plus 1 to n minus 1. It's much faster than exponential function. So the computational cost may be high. And the other problem is the activation energy cannot be measured for every reaction. And if for the simple network, activation energy may be measured, but for large scale, 100 or 1,000 reaction network, we don't know all activation energy for reactions. And so the question is, how can we analyze the temperature dependence of the network level reaction rate in large networks? To analyze this, we use central limit theorem. The formulation is we assume each reaction is Arrhenius equation. And for analysis, we define the inverse temperature. The inverse temperature is here. The function is here. K1 and K1 0 is the reaction rate at a reference temperature. And then next, I will explain the derivation of the large network level. But I think it's very complicated. So first, I show the conclusions. I will explain them, but the main conclusion is log of reaction rate is quadratic function of inverse temperature. So Arrhenius plot should be quadratic. This is the main conclusion. And then we derive this. We need to use some trick. Here's the formulation, and we already know the network level reaction rate can be written here. And we define the ZT and VF. ZT is the ZT is numerator of this equation, and it can be written Kij exponential minus delta Eij, and ZF is denominator. And then we analyze the temperature dependence of ZT and ZF. And here is the definition of ZF as ZT. And the ZT can be rewritten here. It's the same. Kij is will take log, and it's in exponential function, but the same thing. And then we define ET and KT. ET means summation of Eij activation energy. And KT is the product of the reaction rate of at the reference temperature. And then ZT is parameterized by dummy parameters A. A is dummy parameter, so not biological name. We just put like here. And if A equals 1, ZT is equals original ZT. That's to analyze we introduce these dummy parameters. And take the Taylor series of log of ZT of A around A equals 0. And log ZT becomes here. And when A equals 1, log ZT becomes original log ZT. So log ZT can be written here, like here. So it means if we know we analyze the partial derivative of log ZT, we can obtain the original log ZT. So next we analyze the partial derivative of log ZT.
Sorry, equal 0 or 1?
For Taylor expansion,
Around 0.
Yeah, around
and
0.
then log into 1.
yeah.
Okay.
And then partial derivative by definition, partial derivative of log ZT is written here. And then we assume ET and log of KT0 are independent. It means summation of the cross term equals 0. And then this exponential can be separate because the cross term is 0. So, and the first term is temperature dependence, and the second term is constant. It's not dependent on temperature. So we focus only on the first term. We ignore the second term because it's constant. And if the network size is very large, the summation of exponential minus A delta beta ET is number of spanning tree times expectation value of exponential minus A delta beta ET. So if we know, we derive the expectation value of this function, we can analyze the temperature dependency. But how to do it? Using central limit theorem, we assume the activation energy follows Gaussian distribution. It's natural assumption if the network size is very large and non-biased. And if we assume the activation energy follows Gaussian distribution, the probability density function is Gaussian. And then expectation value of exponential minus A delta beta ET is here. Actually, FT is Gaussian. And then this equation can be written here. And this term is also Gaussian. So this integration is 1. The expectation value is simply exponential minus beta delta beta A plus 1/2 times here. Then log of expectation value is simply quadratic function. And then substituting this equation to the definition of partial derivative of log ZT, it's partial derivative of quadratic function for each n. For n equals 1, this term is linear function of inverse temperature. And for n equal to quadratic function of inverse temperature. And for n is larger than 3, partial derivative is 0. It's constant. It's not temperature dependent. Then we know log of ZT is quadratic function of inverse temperature. So for large networks, and if we assume central limit theorem, it is Gaussian distribution, log of ZT is quadratic. And similarly, log of ZF is also quadratic function. Same analysis. And then we finally conclude log of reaction rate is quadratic function of inverse temperature. This is the conclusion of this theory. So it means the Arrhenius plot should be quadratic. So let's check the simulation. For small network, the component network size is 20. It's not so large. In this case, the histogram of ET did not follow a normal distribution. It's slightly biased. slightly different from normal distribution. So RNA's profile was slightly deviated but nearly linear. And for large network, the network size is 1,000. The histogram nicely followed Gaussian distribution. In this case, the RNA plot was quadratic, as we predicted. We confirm this theory is correct for numerical simulation. And then we compare the experiments of development of Drosophila embryo. The vertical axis in this figure, vertical axis is a 1/time from A to B. It's not so separated. It's not for so far. So the experimental value is slightly quadratic, but not so bending. But the right panel is from stage A to stage K. It may be the network may be very large. In this case, the experimental value nicely followed the quadratic function. So the conclusion is the temperature dependence of the developmental rate can be well fitted by a quadratic function. Summary, in this paper, they derived the network level reaction rate using graph theory. And for large networks, their plot is quadratic function of inverse temperature. And this prediction is validated using numerical simulation and experiments. That's all. Thank you.